Thank you very much. I would like to thank you, the organizer, for giving me the opportunity to speak here. I'm very much impressed because usually when I talk about this stuff, it's in front of a room of 10 or 20 people. So yeah, I apologize in advance if I'm a bit shaky. But as you can see, I've used cutting-edge technology for slideware, which is called Emacs. Actually, I don't have slides. Everything is about code, so I will show you code. This talk is titled Event Sourcing Functionally. It draws on my experience developing a system in Haskell over the past 3 years for 2 different companies. I would like to give you to show you how a pure functional language can actually helps us model better model a domain and provide some interesting tools to build event source systems. And I would also like to hint at how Haskell, the Haskell ecosystem, and the type system can really be helpful to build strong, flexible, and maintainable systems. I think that, like most speakers, I'm trying to cover too much ground, so bear with me. I will try to keep a few minutes for questions at the end, and I will stick around for the whole day. So if you really want to get into the gory details, I'm available for you. Okay, so let's start. So my name is Arnaud. As you can guess from my accent, I'm French. I have too many years working in Java. I have also some years working in Haskell. I've been coding with it since 2001, but doing it professionally for about 3 or 4 years only. I used to be an agile coach. I don't do it anymore. And right now, I'm the CTO of a startup, globalspace.co, which is building a system to help teams and small companies get better offices and manage their offices. And the system I will be talking about is actual code I'm using in production now. Well, production. This is not Twitter, of course, but okay, let's start. So this talk is really, I'll just go through a first demo code. So this is basically the kind of code I write every day, but with a very simple business domain. And I will try to hint at some characteristics of Haskell in the passing. So yeah, I mean, that's boring stuff to make the compiler happy. So let's start with the interesting thing, which is writing a test, right? This is where everything starts. So the kind of test that we can write is Haskell. Here we'll write some property-based testing. I guess that quite a few people here attended the property-based testing session by Romeo Mura yesterday, so you know what I'm talking about. And what we will be doing is defining the basic properties of a very simple model, which is a bounded counter. So here we are talking about a bounded counter, and this counter, so the idea that when we apply commands, then basically the end result should be a counter which respects its bound, and the converse property that we should not apply commands that result in the counter going over its bounds. So what does it look like? Those properties we can express. The first thing I usually do in Haskell is that I try to express the properties of my domain model, my business domain, or however you call it. I just say model. And these properties are actually expressed in pretty much in code. So here we say, okay, we have a command. What kind of command we would like to do to apply on the counter? Well, basically we have 2 commands. We would like to increment the counter, and we would like to decrement the counter. And if we increment the counter, Well, basically we say that if we start from an initial counter, which is what this line says, and we apply our command on this counter, then we get the counter with the same number that we apply. Starting from 0, if you add n to 0, you get n. That's basic arithmetics. And the nice thing, the interesting thing is that I lay here the foundation of the two functions that are really at the core of the model I'm using, which is act function and apply function. And the act function says, okay, I take a model, I take a command, and I return an event, which is produced by the command. And the apply function, which takes an event, a model, and returns an updated model. So this is really the core stuff, and this is what I basically do with my model. The two main functions, and init is just a way to start with an initial model. So, and the decrement property is quite straightforward too. We just apply a counter with maximum bound, and we get the result back. Okay, very easy, nothing. And then the negative property, which says we shouldn't apply a counter over its bound, it just say, okay, if I take a bunch, if I got a bunch of commands, so I have a list of commands, so several commands, and I apply all of them on my counter, then I should never get out of the bounds I fixed for the counter. So the bounds here are fixed by the property, which are between 0 and 100. Two interesting things here that are probably not that's very easy, that are very common in Haskell and that are becoming mainstream in other languages, is the fact that I express properties and I can generate samples using the quick check framework from that. And my properties are actually, they are not proof, basically, because I will need some more powerful type system for that. But they're actually a way to express strong invariance about the domain I'm trying to model. And I can really generate a lot of different things and a lot of different commands to get to my model. Yeah, it's already getting a bit hairy. I'm sorry for that. Okay, now the meat of the model. What is a model here? So first, we have some types, some data types, actually types which carry data in our system. So the data, the structure of a data for modeling a counter is pretty simple, right? It's something like an int, basically. But because we don't like, in Haskell, because we have a strong type system, we don't like to do primitive-based programming, right? We don't like to do stringy programming. What we use is all the time, and as much as possible, we use really actual types. This is the reason for the new type keyword is. So a counter is an int, but what I do is I wrap an int inside a very specific type, and then from now on, I know that if I'm talking about a counter, I'm talking about a counter, not an int, not an arbitrary int. This is a very simple model. We could imagine that our model could, for example, take into account the bounds or whatever. That's just to get the idea of it. Okay, so now the three interesting things that are really at the core of an event source model, actually the way I understand it, is that we have commands. We have commands that are specific to our model. This means that because of the type system we have in Haskell, we can say that I can only apply and I can only use specific type of commands and not other types of commands. We have events, so which are the result of the application of a command on the model. And we have errors, because I lied when I say that an act function actually returns an event. It actually can return either an event, which will modify the model, or an error, which says, well, I cannot apply the command to this model. Then we have the actual data definition of the counter, the events, and the errors. And we can see here that we just basically model two errors. The out of bounds error, we say, okay, well, you cannot apply that command because you are going out of the bounds. Obviously, we could make it more specific with the bounds that is broken. And we have a more generic system error system error that will be whose usefulness we'll talk about a bit later on. Okay, so far so good, I guess. That's pretty easy to grasp, even if the syntax is weird. Now, how the implementation looks like. So this is where things start to become really interesting. Is that every model in my system, in the system that we are building, is actually an instance of some interface. Actually, it's not an interface; it's what we call type class, but it's basically the same thing. With a bit more power inside. So what we do with the model is that we can do three things. Get an initial model. So here our initial model is simply a counter with 0 value. We can act, and this is where you can see the actual type of our functions. So the act function takes a counter, a command for a counter, and returns a result for a counter. The result type actually wraps the fact that it returns either an error or an event. And if you get the definition of our domain model, it's pretty straightforward. I mean, even if you don't know Haskell, I'm pretty sure that you can read it. You get a counter with some value, you apply an increment or decrement command, and then you check your bounds. This is actually where the business domain invariants lie, where you actually will do all those checks and all those business level knowledge that are really relevant to only your model. And then you return something which is either an event to be applied, it's okay, you can add the value, or an error, which is KO in this case. The interesting thing is that we can see here that the language of the command doesn't have to be reflected in the language of the events, right? A command can be an increment and decrement, but here in the end it just generates one event, which is added. And we add a negative or a positive value depending on the increment. Obviously, it all depends on the domain you are modeling, what kind of language you will be using. And that's really the core of it. And that if you only get one idea out of this talk, it's that with Haskell, it's very easy to start to use and to model your domain using some specific languages, which are really relevant to the domain you are building. And if you start to think about how to design the system, then it's interesting that you can really use the words and the language, and even down to the point where you can use the syntax, the structure of the people with whom you are working to model your business domain, down to the code itself. So that's something I really find valuable. Okay, and now the apply function, which is very simple in our case. We just take a counter, an event, we only have one, and we return an updated counter. So quite straightforward. An important thing here is that events cannot fail, right? Events are something which has passed. They are really a description of the past. So they cannot fail. So there is no outcome about failure. If something fails at this stage, then that's probably something that you need to shut down the whole system. Okay, so maybe we can try. No, maybe we cannot try because I'm just. Oh yeah, and I forgot something important is that at some point I need to, if I want to test properties for my model, I need to tell the software which kind of command I should generate, how I should generate the command. So this is where I define an arbitrary command, how I get an arbitrary command. So if I load that in my code, then I'm probably able to run the specification. So just to be sure that, yeah, okay, so our model respects the specification. We can be a bit more specific. We can actually test the properties that we are talking about. So if we want to just test the properties we have here, so for example, the one that's about applying commands, we can run the quick check, and it says, okay, I have tried 100 commands, and they all pass. And we can even do something a bit more interesting just to understand what's going on. I can generate it verbosely and say, okay, here are the commands I tried to apply. If we do the same with the other property, you can see that it is actually generating sequences of commands. Okay, you get the idea, I hope. This is our domain. So this is really the pure part of our system. Everything here is a pure function. No side effects, no references, no mutation, no whatever. Everything is a pure function. You take commands, you generate a new event. You take an event, you generate a new model. And you have to go through the interlocking of the two functions to get to something. Okay, so now we have a bounded counter, that's fine. Let's expose that bounded counter through a very simple service that other people will be able to use. As usual, I like to start writing tests. So what people can do with our service, well, they can do three things. They can increment the counter, they can decrement the counter, and they can get the current value of the counter, right? If we try to model that, well, we'll just use whatever tool we have at our disposal. We have the language, so let's write the language for describing the user interaction with the system. So for describing how clients will interact with our system. So the various actions that we have, we can get the counter, the value of the counter, we can increment the counter with some value, and we can decrement the counter with some value. And we need to tell the systems, to tell QuickCheck, how do we generate those actions? What are the rules that we want to implement? This is something that's really, when you start to use it, that's really powerful, because with the system, with QuickCheck, and by modeling the interaction with the outside world, using a language of actions and commands, you can actually define your expected behavior and expected patterns of interaction with the outside world. Obviously, for a counter, it's not very interesting. But if you start to think about a real business domain like banking or whatever, postal codes or management of users or whatever, then it's becoming very interesting, because you can actually model the interactions the user will have with your system. And something that I have started doing in my previous company when we started to have users is to actually to extract the operational profile of the interaction we had with the system and to feed that back in our test, saying, okay, we saw that users were trying to use our system this way, so with this sequence of interaction, okay, can we just model how our system will actually, can we test our system with these interactions and maybe try to tweak it and maybe try to be sure that every change we make would actually make those interactions still possible. So that's really a powerful pattern to do. Here we do something very simple. We just apply frequencies, and there is no interaction with the different commands. But you can imagine that you can actually generate a sequence of commands that are meaningful from the point of view of the user. Okay, so what are the properties that we want to enforce? Well, the basic property that we want to enforce is that no sequence of user action will actually break the bounds of the counter. So this is a bit different. This is actually the same property that we had before, but expressed at a different level. Here it's expressed at the service level. And so this is where we start to go into the impure world of monadic input-output operations. But conceptually, it's exactly the same thing. What we do is that we just generate a bunch of actions, apply that to our model, and just extract the value from our model and be sure that the value actually respects its expected state. Or actually, in our case, it respects the bounds that we set initially. So in this case, what do we do that we didn't do before is that we're actually talking to the outside world. We're actually storing the events and using some underlying storage to store the events and to be sure that our model is actually persistent. So this is where all that bunch of code is what all that bunch of code is doing. So we start with we have a storage with default options. The options just tell you where you would store the information, and something I will talk a bit about a bit later, which is the version that we are using. And then we pass this to a function which takes this storage, and then we initialize our model. So our model is actually extracted from the storage. And then for all actions in the sequence, so we will just go through, just think that it's a for loop. For all the actions, what we do is that we interpret the action. So just imagine that we are really modeling behavior from the external point of view. So we take an action that is something that a user or a client will do. So we interpret it, and we interpret it in the language of our business domain, in the language of our commands. In our case, this is pretty straightforward, because basically we are just modeling interactions as a one-to-one relationship with the commands that we have. But this might not always be the case. We can have interactions, and we can have users using our system with maybe with a single action being mapped to several commands, or a single command being mapped to several actions, right? It's not a one-to-one relationship in general. And then this is where the real thing happened, is that we take the result of this interpretation, which is a command, and we inject that command, and we apply that command through some effectful code to our model. And the end result is a bunch of results from the execution of the commands. Okay, so it's exactly the same principle, except that we have a bit of more machinery and plumbing to do to get to make it work. So how do we implement an effectful service on top of a pure model? That's the hairy part. So what I do is that when I started working on that system, I tried different approaches, and I settled on this approach probably 1 year ago, and I found it very powerful and very interesting. So the idea is that, I'm sorry, I will use the M word. The idea that we will use something which is called a free monad. So the idea of a free monad is just to say, I can take a bunch of languages, of small languages. So in our case, we say, okay, my system is something that maintains some state in our model. So this is a language of maintaining state, which basically boils down to two verbs, applying a command and getting the state that I'm talking about. But we also want to be able to raise exceptions. And this is something this is a different language, a very simple language too, which with a single, or rather two verbs, throw and catch. And then, okay, we also want to be able to do some interaction with the outside world. So to use the I/O stuff. And then we need to terminate the chain of language we are composing, and this is where the void enters. So I was really pleased when I saw Rebecca Wirsbrock talking about void later on, because it just fits very nicely with my talk. It's actually the same kind of void, because the void here is actually the neutral element of a monoid operation, which is basically the role that a void, in the sense of theory of centers, it's exactly the same role. There's something around which everything is revolving, right? But which is empty. End of the philosophical parenthesis. And now, so this is a type. This is a type of effects I'm doing, and the type says that, okay, my event source model is parameterized by two things. We have M, which is the type of domain model, the type of model I'm working with, and A, which is the value I can return from all the actions. And now, if I want to run some effect, in my system, then I need to be able to interpret all the small languages I have used. So if I write apply command in my code, then I need to be able to say, okay, what does it mean to actually apply a command? If I say, oh, I want to throw an exception, what does it mean to throw an exception? And this is where I just use the basic design pattern of functional programming system, which is a function, and composing function. So I just compose functions, and the functions, we say, okay, to interpret anything inside my system, I just run states with some storage, and then I can pass the value or the thing I want to interpret to the runner, which is specialized for exceptions, and then I can pass it to the runner, which is specialized for lifting into I/O, if this is an I/O operation. And you can imagine that each of this is a small machine that interprets a fragment of a language and does something with it. So this is, now we have the technical part. So this technical part of the code, which is about preparing the model, it's just where we create a persistent model. It's not very interesting for the moment. I will talk a bit more about it later on. Now, if we want to go to the other part of our interpreter, so we need to tell, okay, how do I interpret actions from the user? So here, in our case, this is pretty straightforward. We can say, okay, if we get a counter, then this is just a command to get a counter, and same for increment and decrement. So this is really straightforward. And finally, we get to the point where we have the definition of the actual service. So those functions that you can see here, so get counter, increment, and decrement, are the actual implementation of our service on top of our model. And you can see here that, well, get counter is simply something that retrieves the counter out of the state. So get state is where I will retrieve the state from our model. And this is something that is handled by our state functor. Increment is something that I apply a command, in this case, increment command, and then I should do something with the result. Same for decrement. And finally, if you look at the handle result command, this is where we actually say, okay, given some outcome from our command, I can have either an error or an event. What I want to do, because I'm talking to the outside world, I want to let the outside world know what happened if there is an error or an event, right? So I just say, okay, if there is an error, this is the first case here, I want to throw an exception. And this is where I'm just saying, okay, I need to be able to throw exceptions. And in this case, I need to be able to throw exceptions using whatever framework for web interaction I'm using in the background. And in the other hand, if the other side of the other branch of the either is what happens if I have an event? Well, in this case, if I have an event, I simply decide to return the current state of the counter to the user, right? Okay. So now, if I load that, okay, so it should be, it compiles. Well, if it compiles, it works, right? That's the basic promise from Haskell code. Well, let's actually check that it's working. So now I will check actually the property for my service. Okay, and you can see here that I'm just generating the same stuff that before, except that now I have something more, which is I have another command, which is the get counter command, which actually is not very interesting in our case because we are not checking it. We are not checking anything about it, but well, just to get to be more complete. And here we have what we have done is that we have we actually run the test against a fully functional service with an existing persistent mechanism. And this is where, so this is the store data here file that you can see here. And this is where the state is persisted. I don't do this for real in tests, in my tests, because obviously I don't want to pollute my test with pre-existing data. So there are other mechanisms to remove that, but that's just to give you the rough idea of what we can do. Okay, so far so good. And the interesting thing when we get to event sourcing is that the basic principle of event sourcing is that we store events instead of storing the state, right? So that's what we do in our store data. This is where we store actually the sequence of events, and when we reload the state, we actually reconstruct the state from the sequence of events. So we need to tell the system what it means to serialize an event. And this technical code says, okay, how do you encode an event? And an interesting part of the system that I did not invent it, but I borrowed it from basic principle of event sourcing is that every event is versionable. What it means to be versionable, it means that when we serialize the events, we attach a version to the event. And this is the current version our model is operating in. And then when we reload the system, we have all those events with different versions, and the system is at some version, hopefully at the head of the version, because the basic principle of version is that they are monotonically increasing. And the system actually handles the different versions by migrating the events to the current version. And this is where the versionable type class comes in, or interface, if you want to say that. It says that what it means to deserialize or to handle the serialization or deserialization of an event given some version. So this is where, if I need to migrate my code, and I often need to migrate my code once it gets into production, then this is where I say, well, this is version 1 event, my current version is version 10, then I need to apply those changes to get to the event. I'm probably preaching converts, but I found this system to be extremely powerful because I've been dabbling myself into database migration scripts, and this has always been a nightmare. So this is a really good way to handle versions across the system and maintaining that into your code. Okay, so so far so good. Now the last part is, okay, no service will be interesting without having a REST API to talk to, of course. So that's where we need to expose our API. So here, once again, we are taking benefits of Haskell's tab system. So I use a framework which is called Servant. And Servant allows you to define your interface and your REST API using types and only types. So your interface is defined as a type with several branches describing all the various endpoints that you want to add, and with the different types of values that can get in and out of your system. And the really nice thing is that once you have that, it's very easy to actually get a client and to generate stuff out of that type. So that's why I like to use this framework, which is becoming more and more mature. And unfortunately, it uses some advanced type system stuff, which I don't really understand myself, but I'm not writing the framework anyway, so that's fine. But I think that the signatures that you get are pretty straightforward. So here we say that we have a counter, we can have an increment branch, and this increment branch will capture some int value and returns an int value, right? Okay, so now I will just gloss over. So same as before, I write properties and quick check tests to test that actually my REST API is working properly. So this is where I'm reusing against the framework. I'm reusing the framework I built before, but now I just build up my system with a real web server and a real underlying storage. So I'm just building up more and more complex tests to work with. I won't go into the details of all this stuff, but the idea is that we are just testing that our server is working. And now, just as before, we need to interpret, our test is modeling actions. So something which is really interesting is that we use here the same actions. So those are the same actions than before. We are just modeling abstractly the interaction from the outside world. But now we are providing a different interpretation. And this interpretation, in the first case, this interpretation was direct call to our services functions. But now the interpretation is actually calls through the REST API. So this is where I need to do stuff like run client M, and I need to define the various functions I will use on the client side to interact with my server. This single line is actually the whole definition of my client. That's where the power of having the type is interesting. So here I have the type of my API, counter API, and given only the type, I can generate, or the framework generates all the clients. And I can just use those functions to interact with my server. The server-side handlers are pretty straightforward. Those are exactly the same function that we had before, except that now we are composing them into the various branches of our system. And obviously, this cryptic operator is here. It's just a mirror of our API. So if we have a branch that is an endpoint, then this branch and endpoint should correspond to some function. But once again, we only do some wrapping. There is no, I mean, all the details of the plumbing and the mapping is done by the types themselves and guided through the types. And there is no error. If at some point I change the type of the return value from int to float, then my system won't compile. And this is really a strong guarantee that we have with Haskell. I will just close that part of the talk with, okay, now we can have a main function. So this main function is just something that will run our server through and make it available to the outside world. So if I load that code, and if I say, okay, I want my server to be running at port 9999, and if I run it, then normally, if things go well, I should be able to interact with my API, my counter increment, or should it be inc? Oh, I'll just do -v. Okay, so this is not found, so maybe it's increment. Yeah, it's increment. And now you can see that, okay, it's a bit hidden here, but you have the value of the counter. If I increment the counter, the value changes. All right. Okay, so this is demo code. How does it look like with real code? I have an example which is interesting, which might be interesting, which is so this is the part of the system that we have which handles user registration and user management. So it's quite simple. I mean, the business domain is very simple. Just manage users and register them. But what's interesting here is that you can see that my event store type, which is not very well named, I should say, but so it's the same type that we had before. But now it's a bit more complex. What we can do is that we say, okay, we have the state, so that's fine. So far, so good. We have the exception, we have the lift IO, and our void. But we added some things in between. We added two things. We added something which is called a user request, and we added the ability to log. The nice thing is that log is something which is generic, so it's just like a cross-cutting concern. If you come from object-oriented programming, think about aspects. It's just a way of composing things, except that those are not magical interfaces, magical stuff. It's just functions all the way down. But with those functions and using the type system that we have, we can actually compose things in a way that is extremely extensible. If I don't use anywhere in my code the logging capability, then I can just add the capability to interpret the logging, but it won't change my code. It won't affect it, and it will compile just fine. But now I can do logging. And user requests is something that's interesting in its own respect, because it talks about it's a definition of the interactions my small service can have with the outside world. So just like everything else, I'm just defining a language. So this is a small language. In objects-oriented in Java, you would probably define some interface to do that. But here we are defining functions, and we are defining a language, and this language is actually composed and made from reified objects, reified values. So we have the ability to send a mail, we can set confirmation mail, we can add a new user that's sent to some other system, and we can get something which is important is that we really do a containment over side effect. So here what I do is that I'm getting a date, I'm getting a new token for the user and getting salt to generate password. And all this stuff is actually something that has side effects, right? It's something, if you want to have to get randomness, you cannot do it using pure functional programming. You need to get to the underlying system. But this is something that I would like to control, and I would like to be sure that I'm doing it in the right way. So that's where it's important for us, and it's important in a functional setting to be sure that everything is actually controlled, and you don't do I/O arbitrarily in the system. Okay, so this is the actual code that we are using, and this is where we are really leveraging the machinery for that are the functor stuff and the free monad stuff. So these are very abstract concepts, but in practice it's very easy. It just says, in the end, I have a bunch of languages, and I want to be able to compose those small languages together. I want to be able to say, well, if I have some event happening or some error happening, then I want to trigger that call to that services, or I want to trigger that call. If I have another event, then I want to trigger some other call, or what. So all this interaction is actually dependent on some result from some previous computation, right? And so by combining those different languages, we get the ability to build a bigger language, which is defined here by our type, which is, okay, now an event store in my user service is something that can handle the state for users, something that can actually interact with the outside world through in a controlled way. I cannot do arbitrary stuff. I can only do limited stuff. I can do logging, which is interpreted in some way, and I can throw exceptions, and I can do IO actions. And now, if we look at how the model looks like, well, it's also quite simple. Just my model here is it's simply a bunch of maps. So here I'm just mapping the users by ID and the users by token. One main characteristic of the system is that all the state is maintained in memory, and that's something which might be obvious or maybe not. When I'm giving this talk to people, usually I get the question, so I really answer the question. Well, did you think about performance and how much space will it take, and what about RAM and whatever? I say, okay, yes, this is a good concern. This is a good concern to have. This is a concern I don't have now, given the amount of interaction that we have and the amount of interaction that we foresee. So, and the maximum amount of RAM that I can have on a single machine in the cloud is something like 96 gigabytes of RAM, which will host a whole bunch of users. So by providing different services and by dividing my services along very strict boundaries, very small models, then I can just distribute them, and I can just scale up very easily, because each service can be as small as I want and host as much data as I want, so it can be reduced, or it can, if really I need to, I could even imagine doing some sharding stuff, right? Just distribute everything with sharding. So it's not really a concern. What in the case where it would be a concern is that if I need to do a cold restart and I need to rebuild all my system from scratch with a huge log, but then we can use techniques like snapshotting or stuff like that. Okay, I think that I'm running. Just to give you some wrap up, this code is available online on GitHub. So this is open source code. For those of you who prefer slideware, which might be a bit less aggressive stuff, I have made available slides. So this is a similar talk, but it's a talk I give in a more structured, or maybe a more with less advanced people. I've been told that DDD Europe is for advanced architects and developers, so I mean, let's talk about real code. But in other settings, what I do is just I just give slides. You will find the slides inline, and it gives you more context. It also gives explanation about what event sourcing is, which I don't think is relevant in this setting. This is still pretty much a work in progress. And there are a lot of areas I would like to explore based on this system and based on these settings. Couple of things I would like to investigate is the storage part. Storage part is currently done using flat files, which is simple and cool, but which might not scale that much and might not be resilient enough. So I'm trying to explore alternatives like using a Raft or a strongly consistent backend. Because I've been working in fintech, I mean, my previous job was in a company which was doing crowdlending. I'm pretty much interested in how we can make, how event sourcing can be used as a way to audit and to enforce transactions and to actually provide a proof that something has actually happened. And this is where I would like to, I know there are works which try to apply the cryptographically signed ledger to this kind of stuff. So that's one direction I would like to use, especially when we will want to interface with other people and to interface with other systems. It would be really interesting to be sure that, hey, when something happens, and when you send me a command, I can get your command and get your key just down to the event store, and I will use your key to sign the events, so that we will be both sure that this happened, and this could only happen this way. And the last thing I would like to do is just improve the bootstrapping and boilerplate handling stuff, but that's really just usual software engineering. Okay. Thank you very much. So I mean, I could go on talking about this for probably days and weeks. We don't have days and weeks. Maybe we can keep some time for questions. I'm afraid that a few people have fled out of this room. I don't know if the others who are still here just are too polite or are actually interested in that stuff. Yes, we have a question here.
You mentioned that if your server went down, your application crashes, you have to replay the log.
Yeah.
Have you ever had to learn for that? And do you have the tooling to rehydrate the model?
So can you, sorry, can you repeat the question?
Of course.
Yeah.
Do you have the tooling to rehydrate your model based on the event store if your server crashes and you basically have to replay all the events?
Yes. Well, that's what we do all the time.
Okay, so do you have tooling that you can...
This is all baked in the, it's actually the function I glossed over, which is the make persist function. So this is, I mean, I didn't go into the gory details of how it works, but basically when you build a model from the underlying storage, the whole storage is reread, and we replay the log.
And you do have tooling for that, and you went through the effort of doing that.
Yeah, I just do it. So there is no special. I mean, I'm not sure about what you mean by tooling, because in this case.
Well, I mean, do you have, like, is it just an endpoint that you send it off to? You have command line utility that you fire off to?
Yeah, that's the idea. So I implemented two different storages. So there is one which is just file-based persistence, so very local. So we just write the events. When we reload, we read the file and rehydrate the model. And there is another storage, which is REST API for storage, which can actually be like a tree-shaped or whatever, and which uses the file storage in the underlying system. But it's just it's a single load command, which uses the same mechanism than the rest, which is just one. It's a functor which is wrapped in a free monad that you can reuse. Just the same mechanism. But I don't expose it at the service and domain level. But you could. Yeah, so the question, sorry. The question was about if there any tooling to support and to help into the rehydration of the model in our case. Yeah, if there is another question, don't be shy. Yeah?
So my question is, how long it takes to reload the system to dehydrate? Because of if I make a change in the code, for example, and I want to deploy it to production,
Yeah.
so then how often, if I do it often, then probably I should be able to restore the state quite quickly.
Yeah. Oh, so the question is, when you're doing migration, how often do you have to restore the state, and do you have to restore the state when you're doing migration? That's your question?
How long it takes?
How long it takes?
Reload.
Yeah, okay. So how long does it take to reload the state? I will give you the usual answer. It depends. In my case, so in my previous company, we were doing, we were doing crowdlending, so we had about 1,000 or 2,000 users, investors. So we didn't have that much interaction. The whole ledger, so the whole log, and in that company, I didn't have microservices, so everything was a single log. I think that the whole log was a few tens of megabytes large, and it took, I mean, I never cared to measure because it was below, it was sub-seconds. It was sometimes noticeable when, because Haskell is a lazy language, right? So when you do something, if it's not needed, it's not evaluated. So when you radiate your model, if you don't need the value in your model, then the various sequence of events are not reapplied on your model. So this can be a bane or a boon, but in our case, it's more like the second, because actually, as long as you don't interact with the model, then you don't pay the cost, right? And it's only on the first interaction that, well, you will replay down the whole log. I think that right now, our system is just starting up, so it's not it's really milliseconds or stuff like that. But I guess if we grow, and I hope we'll grow, but if we get into the gigabytes or tens of gigabytes or even hundreds or terabytes, I don't know. Yes, at some point it will be a problem. But then really it's very simple. It's a very simple problem to solve because then you can use snapshotting, right? And and at that point, I guess that we will use some real database that will just remove the problem from our end. Something like, for example, I can imagine like Kafka, which is very well suited for that kind of stuff, just storing distributed ledgers. And they have the system of snapshotting that you can reuse. Thank you very much for your attention.